Chapter 10. Let's do a little reaction review here. I think this is good to go through and kind of work a quiz together, you could say, as a class. So we need some help here, and hopefully, you can look at these and try them along with us. If you want to pause the video, or we'll take some time here live to look at these. So examining the conditions and what type of alcohol it is. Remember, chapter 9 was the alcohol chapter, and we learned a lot about what dehydration reactions and substitution, converting the alcohols into other things like halides. We did halogenation of alcohols, and we did tosylates also. And we did epoxides. Yeah, we got a couple epoxide reactions here to review too. So it's kind of a diverse chapter, that chapter 9. So it's a good thing to review here. So if we have a tertiary alcohol with strong dehydrating conditions, sulfuric acid, where are we going to get? We're going to get the alkene. And where are we going to put the alkene? Are we going to put it up here, disubstitute alkene, or right here on the side? How many people say on the side there? Okay, yeah, most people. Yeah, so that's our major product for that one. Now, this one is a secondary alcohol, and it's branched at this position. So we've got an issue there. We can kind of go through the mechanism to think about this. So after we protonate and get the secondary carbocation, what can occur here? We can have one of these alkyl groups shift over, right? And then we can end up with the double bond, there, after we shift over one of these ethyl groups. So hopefully you can see that as the product after a 1-2 shift, tertiary cation, and then we lose the proton right there to get the tetra-substituted alkene product. So that one's a little bit different. And then let's see here. We've got an alcohol with a stereocenter. I think that is the R in enantiomer. Now, sometimes that's important. Sometimes it doesn't matter, right? Sometimes the stereochemistry goes away. Well, let's see here. POCl3, and that should be with pyridine. Sometimes we leave it off. If you leave off the pyridine, we'll still give you full credit, but it's POCl3 with pyridine. And we're going to do also dehydration here. And are we going to form the double bond over here or right here? Let's see. So, yeah, it's going to be this one. And we have the choice there between cis and trans, right? Because each carbon here has 2 different groups on it. So this is trans butene, okay, that we're going to form there. Not 1-butene here, okay? And then HCl, if we treat this with hydrogen chloride, strong acid, but now we have the chloride anion as a nucleophile in there, right? So we're going to form the carbocation like before, but then chloride can go on there. And yeah, this will be a secondary carbocation after we protonate and eliminate water. And then notice this is R, but now it's flat here, achiral, right? So the chloride coming in on the top or the bottom will give us what? A mixture of enantiomers. So you'd say DL there, plus minus for that one, okay? Question on any of those so far? You guys doing okay? You getting 100 on this quiz so far? No, it's not a quiz. Just for the fun of it to review chapter 9 here. There are a lot of reactions though in chapter 9, right? Yeah.
So generally, like the alcohol, when you're reacting it, like in the presence of the purity, why is it that alcohol is the eliminator when the sulfur SOCl2 tends towards substitution?
Yeah. Okay. Yeah, so this forms a phosphorus-oxygen bond. Remember, it turns it into a good leaving group, like thionyl chloride. We could look at the thionyl chloride one coming up here, PBr3, or thionyl chloride up here. And that's very good. So the pockle here forms the phosphorus-oxy dichloride leaving group here, okay? And in the presence of pyridine, that's a good enough base to do the elimination, okay? So yeah, you kind of have to remember there. Yeah, now pyridine's not a very good nucleophile, and yeah, we do generate a chloride here, but this combination of reagents, this reactivity combination, is such that it mainly gives elimination. Now, I did show you a panel where I showed you Pockle did give some substitution with primary and tertiary. Really, Pockle is best just with secondary alcohols. But that's kind of a gray area thing, and I'm not going to expect you to know that kind of stuff. If you see Pockle PLCO3 with pyridine, purposes of our class, do an elimination. That's our major product, the only one you need to worry about. But you're correct. I mean, you convert it into a leaving group, you do have chloride there, and you could think about substitution instead of elimination. So very good. So the question was, why do you just get elimination here? And it's peculiar to that combination of reagents. Okay. Yeah. Okay, let's see. PBr3 up here with that same R alcohol. What are we going to get? We're going to get substitution. Okay. And that's clean inversion of the stereochemistry. So it's an SN2 type reaction. After the phosphorus forms a leaving group here, and the halide under these conditions is good enough to do that. Same thing with SOCl2, right? Thionyl chloride would also give the substitution backside attack, the S chloride in that case. Here, the bromide from PBr3. All right, turning alcohols into a good leaving group would be the tosylate. So after this first step here, we'd have this tosyl group on there, and that's that big paratoluene sulfonyl group. So this is like a sulfate or a sulfonate sulfur leaving group with a resonance stabilization. So any good charged nucleophile here will do the backside attack. This is secondary. So azide, for example, gives the SN2 reaction. Okay. Yeah, and that's combining ideas from chapter 7, right? So some of these things continue on. But for test 3 here, we're just testing on the key reactions we're learning in these 3 chapters. Okay. Let's see, HCl and the tertiary alcohol. So what's that going to go to? You might think, well, we just did, strong acid, sulfuric acid with a tertiary alcohol. That gave elimination, dehydration. But in this case, you have a good enough nucleophile to jump onto the carbocation. Okay? So we halogenate alcohols under those conditions. All right, and then we got cyanide here, which is a charged nucleophile. So where is it going to want to attack? The primary position here or the secondary position? Which attack's going to be faster on that epoxide with a charged nucleophile? How many say the primary position? Let's see. Let's get a consensus here. Okay, about half. How many say the secondary position? Okay. Now, what type of a nucleophile is this? This is charged. If you have a polar aprotic solvent, it's going to accentuate that. So that's what type of nucleophile? SN1 or SN2 nucleophile? SN2, right? So that's going to favor attack at a less hindered spot, right? So actually, we're going to get this, pop open the epoxide. And maybe let's show the part of the mechanism here. We'll have the cyanide there. Then we'll have this O minus. And that ether, because it's a small 3-membered ether, is reactive. So you can get this, and then you put in water here, and the water will donate a proton there. And what do we get? We'll get the cyanide alcohol with that stereocenter still in place there. Okay, we didn't invert that one. We attacked here. We did the backside attack at the primary spot. Popped open the epoxide that way. Okay. Now, a couple of complementary conditions here. Let's open this epoxide with methanol under acidic conditions. So sorry, running out of space here. The first conditions are considered methanol with sulfuric acid. That's going to go what? Via this. It's going to protonate the epoxide with strong acid, right? And then break open the epoxide to give them more substituted carbocation, right? And that's flat, achiral, so the stereocenter just went away. And then methanol can attack here, and then loss of a proton. What are we going to get? We'll get the primary alcohol and the methyl ether at that internal position. Okay. That's the more substituted carbocation pathway. So that's like an SN1 reaction, you'd say, right? as opposed to this with the charge in file is more SN2. Okay. Yeah. And then if we do the same reaction with sodium methoxide and methanol, so here's our charge base, and that's going to want to favor what? Again, the SN2 pathway, and that's going to give us what? It's going to give us the methyl ether right here at the primary position, okay, instead of at the secondary there. And then what about here? When this pops open and then grabs a proton, so I'm not showing the rest of the mechanism there. It'll have the alcohol here, and this will indeed be the R. And this one would be the DL, okay? And this one's what's still R also. So epoxides are a little tricky that way, especially when we consider the different complementary conditions, either acidic conditions or basic conditions, and then the regioselectivity, how they can open up. Yeah, another question.
With some of the epoxides, I see the strong acid go on top and the other compound on the bottom. Does that make a difference, or since it's already a solution, what is that?
Yeah, so these are added together. So the question is, when we have the acid conditions or the base conditions, yeah, here the arrow has both reagents. I think that answers your question. So the methanol's in the presence of the sulfuric acid. Okay.
I mean, sometimes I see the sulfuric acid on top.
Oh, yeah. The question is, sometimes we see the acid on top or the alcohol at the bottom. It doesn't matter. They're both there on the arrow. They're both exposed to the. When you see a slash here, that means this is added later. Okay. And that's added to protonate, the alkoxide intermediate. So yeah, sometimes we have, an order of how we add things. Other times they're both in there together. But yeah, we can flip these sometimes. That was the question there. This person was asking about if it's on the arrow, top or bottom, does that matter? And the answer is no. They're both in there together. Okay, questions. Hopefully that was helpful to see some of those reactions. Let's go to the overhead here, Jesherin, and see what we need to know for chapter 10. There are 5 new reactions here, and they all begin with H. So this is a good way to keep track of them, okay? We'll begin with some standard stuff, talking about the structure, degrees of unsaturation, how many double bonds we have based on the empirical formula here. We'll do naming and properties and some interesting alkenes, including lipids, fatty acids. Preparation, we've already learned how to make alkenes a number of ways, right? Elimination reactions. So a lot of this will be review in a way, okay? And a lot of it's descriptive, but you need to know the terms. That's why I put them all here in the outline for each chapter. But now here we start the reactions. So the pi bond is going to be replaced with some reagent X and Y, and that reagent's going to be electrophilic. So actually the alkene will always function as the nucleophile in this case. The reagent is the electron deficiency. So here's our first one, hydrohalogenation. I told you they all start with H, and there's 5 of them, so we can kind of keep track of them here. Hydrohalogenation, what does that mean? Well, we put hydrogen and a halogen across a pi bond here. So if we have ethylene, we'll get carbocation and then the halide. Okay, so we're going to an alkyl halide from the alkene. That's just the reverse of what? An elimination reaction, okay? But here we're using the strong halogen acid with an alkene, okay? And then we get a carbocation intermediate. Now, this will depend on rearrangements and the regioselectivity. We'll have to examine the structure of the alkene and see which carbocation will be the most stable pathway. And that'll tell us where the halogen will go, okay? So anyway, hydrohalogenation. Markovnikov, there you go, another famous Russian chemist at the University of Kazan, along with Zaitsev, and Mendeleev was there for a while too, the periodic table guy. So 3 very famous Russian chemists. His was an empirical observation that the more substituted carbocation is the one that ends up with the halogen, okay? Or the halogen goes to the more substituted carbon position. He didn't know about the mechanism of the reaction, so you'll know more about this reaction than Markovnikov did. But his observation of the selectivity still holds. Stereochemistry, we'll talk about that also. Okay, the second one's hydration. I told you they're all H names, and that'll kind of help you keep track of it. Hydration, what does that mean? Adding water across the pi bond. Okay, and that's just the reverse of dehydration, right? And now that was not exothermic in that forward direction before, but now it will be exothermic in this direction. Why? Because we have excess water. We still have the acid to protonate the alkene, form the carbocation, and then we get the more substituted alcohol product. Okay, that's called hydration. Okay, that's two. And then we got halogenation. This is different than hydrohalogenation, right? Here we're not adding hydrogen, we're adding both elements of the halogen across the pi bond. So we go here with X2, chlorine or bromine, the molecular form, to form what? Dihaloalkanes. Okay? And there'll be a new intermediate here. This cationic thing is a bridged halonium ion, we call it. You could say it's a resonance structure of a carbocation and an alkyl halide. I'll show you that. That has some consequences for the stereochemistry. It's always an anti-addition. It always gives the trans product if it's on a cyclic alkene. Okay, so there'll be some stereochemical issues there with halogenation. And then we got a funny name here, Halohydrin. That's kind of an archaic term that has to do with halogen alcohol. And this is where we do a halogenation, so there's Br2 or Cl2 in the presence of water. The water can intercept this cationic intermediate and pop it open with water functioning as what? A nucleophile. And that will give our alcohol halide. Notice all of these involve 1,2 additions. The 2 carbons involved in the alkene, those are the ones that get substituted, okay, or added to, right? These are addition reactions. Yeah, we're not taking anything off here. There's no leaving group. It's just pure addition to the alkene product. Now let's see, what's that, 4? Yeah, okay, we're up to 4. 5, hydroboration. Oh, there's our first other atom, you could say, boron. Yeah, there it is, borane, BH3. That's Lewis acidic. That's before carbon in the periodic table, just to the left. So it's Lewis acidic. There's an empty orbital here that can interact with the pi bond and then deliver hydride over here to the alkene and give a borane intermediate. The borane gets oxidized with peroxide and base to go to the alcohol. Now, wait a minute. We just did a hydration reaction to go from an alkene to an alcohol. Why are we learning another one? Well, hydroboration has complementary Markovnikov selectivity. In this case, we'll always form the less substituted alcohol product. Normal hydration of alkenes gives us the more substituted alcohol, the Markovnikov alcohol. This is the anti-Markovnikov alcohol, we say. And you'll see that with more complex examples. Now, we'll keep track of these things. The common mechanisms all involve electrophilic reagents getting attacked by the alkene nucleophile. We'll look at the different functional groups we can produce here. And we'll do synthesis. We'll start with alcohols or halides, do eliminations to alkenes, and then use the 5 reactions here to make various products. So it's kind of a multi-step thing that we can begin to do there. All right, let's look at the structure of alkenes and get into this. Some of the basics here on the board. Going back over here. And this is a lot of review. Maybe the details of some of the naming things will be new here, but a lot of this should be review here for you. So what is an alkene? Okay, so, alkane had an A there, so the name with an E implies a double bond, a pi bond. And what is this exactly? Well, the carbon, of course, has a sigma bond, and then it has left over, p atomic orbitals, and then whatever else is on there, is part of the sp2. These are all sp2 hybridized bonds coming off here, including this one, right? The one that's not hybridized is the empty p orbital here, but when we have the electrons in it, right, we've got this overlap top and bottom, and the 2 p atomic orbitals are in phase. We call that the pi bond. If they're out of phase, that's the pi star bond. Bond angles here, theta, 120. It is trigonal planar. And, that should apply to more than just the two carbons here. How many atoms in an alkene are actually planarized? Well, it's this one here too, right? And that one over there, of course, that one, and then that one and that one. There's actually 6 atoms, okay, that are planar, that are held fixed in that position there. Now, this is an electron-rich position, right? This pi bond is filled with the 2 electrons. Now, that's going to function as our nucleophile, okay? And it's going to react with electrophilic reagents. Okay, you can already get a little feel for that. Normally, nucleophiles, so far we looked at, have a pair of electrons or a negative charge on them, right? But here we're going to pull out the pi electrons and attack the electrophile to do our 5 reactions here. It's a relatively short bond. What is it? 1.34 angstroms. A typical carbon-carbon single bond is 1.54 angstroms. An angstrom is 10 to the minus 10 meters, very small dimensions, nanometer dimensions. Why is a pi bond shorter than a typical carbon-carbon single bond? Should think about that. Well, how many electrons do we have here? 2 in the pi bond and 2 here, right? And the dimensions here are dictated by what? The mutual repulsion between the positively charged nuclei. If we have more electrons between the 2 positive nuclei, they can shrink down a little shorter, right? So the more electron glue, you could say, that we have between the 2 positive nuclei, the shorter that will be. And we'll see the same thing with the alkynes. Okay, so we have things like ethylene, which is a gas molecule. Ethylene is the common term for that. If we have larger alkenes like hexene, that's indeed a liquid. We can have cyclic ones, of course. And in a cyclic one, it's almost always a cis double bond. We'll get into the geometry of double bonds here in a second. But cyclohexene is strain-free. Cyclopentene is strain-free. It's not too much of a deviation from 120 degrees. But when we get to something like this, cyclobutene, we have a lot of strain, right? That's constrained to be 90 degrees here. That's a big deviation from 120. And then cyclopropene, even more strain. Now let's look at the geometry here. So here we have a simple alkene 2-butene where there are 2 different groups on both carbons. And so we have 2 geometric forms. We've already talked about this. This is the trans one. This is the cis one. Are these equilibrating? Can these exchange? What do we say about this? So the trans form here versus the cis form. If we start out with the trans form here, got that hydrogen to the front, hydrogen in the back. And in order to go over to the cis form, what would we have to do? We'd have to rotate around the pi bond. Can we easily do that? Let's see. Let's rotate like halfway here. See what happens. Got this rotating here like this. And what do we see there? Sorry. If we rotate that around this bond 90 degrees, we don't have the pi overlap now, right? And so we say, under normal conditions, that can't occur. Well, how much energy is associated with that rotation? What's the pi bond worth? Well, it's worth about 60 kcals. Sorry. So at room temperature, we only have available, thermal energy of about 25 degrees, 25 kilocalories. So we don't have enough thermal energy to rotate around this bond in normal conditions. But we'll see some examples where we can equilibrate these. In fact, the fission process with rhodopsin, we'll see, is based on this. If there are things we can do here, like shine light on it, okay, and it has to be the right frequency of light. If we can do that, we'll convert this into a diradical. We can uncouple the pi bond here, okay? And then in that higher energy state, we call that when we fill the pi star position at antibonding orbital, then it can rotate, can go over to the cis, okay? So the dogma is, you don't interconvert cis and trans alkene double bonds, but we couldn't see if we couldn't do that, okay? So that mechanism of harvesting light has to do with this. So, you got the pi bond here, and that's where the 2 electrons are, but we also have the pi star, right? And if we shine light on it here, h nu, that's a photon of light, okay, with the right frequency, whatever, we can uncouple that and promote an electron to the higher state. And the sum of this two means no bond, which allows for the rotation there. So that goes a little bit beyond what the book is talking about. Now let's look at the stability in general of alkenes. Monosubstituted are less stable than cis disubstituted. Trans are more stable. More stable are trisubstituted, and then tetrasubstituted are the most stable. So what do we do that? We can see that in the heat of formation, and we have a choice sometimes which double bond we're going to form. We always want to form the more substituted double bond. And why is this? Why are these more stable? Well, this has more sp3 hybridized carbons nearby to donate into the sp2. The sp2 carbons are more electronegative, okay? And so they're polarizing the electrons toward themselves. So this is partially positive, partially negative here. This is very small, though. These are very weak interactions. But if you have a lot of them, this inductive effect can be important, this difference in electronegativity. And that's the percent S character, right? More S character here, 33%, is polarizing those electrons in the pi bond, or the sigma bond, sorry, the adjacent sigma bond, a little bit closer to this nucleus. Okay, that's called the inductive effect. Has to do with the electronegativity. And then we also have this effect, right? We have adjacent sigma bonds if we have a lot of carbons nearby here, which are filled, right? There's 2 electrons here. And then we have the pi star here, which is the empty part, the antibonding part of the pi bond. And if they're adjacent here, we can have this temporary interaction between the filled sigma bond to the empty pi star. What do we call this sigma to pi star interaction? Starts with another H. Let's see if someone remembers it. Yeah, hyperconjugation. Very good. Okay, hyperconjugation. It's a temporary thing, but they can be conjugated there. Let's see, in medium-sized or small rings, we can never really have a trans double bond. Try to do that with your models sometimes. Try to make trans cyclohexene. You can't do it, okay? They're almost always cis, and we don't even need to talk about cis or trans in medium-sized rings. It's always cis. That's a stable form. The only form you can get up to here where you can see the trans is trans cyclooctene. Okay, and that is known. It's much less stable than the cis cyclooctene. And this one is what? 1, 2, 3, 4, 5, 6, 7. This is trans cycloheptene, which has actually been made, but it's highly unstable. It falls apart very quickly. And you can see if you make a model here, you have to elongate these bonds quite a bit to accommodate this trans geometry here, okay? So most medium-sized small rings are always cis. You don't need to worry about it. Okay, degrees of unsaturation. This is an important concept. Degrees of unsaturation. And what do we mean here? We're talking about, how many hydrogens are removed relative to the maximum amount in the structure. So here's our typical structure, right? In fact, that's the maximum amount you can have for a given molecule. Okay, so in the empirical formula, we can tell just by examining the number of hydrogens versus the maximum amount, and that will tell us what? How many rings or double bonds we have, okay? Which is a very useful thing to know, especially when we look at spectroscopy, mass spec and NMR coming up. So an important topic there. Let's see. This degrees of unsaturation then looks like this. We have 2n plus 2, that's the max, right? Minus the actual divided by 2. And that will tell us the number of double bonds and or rings we might have in a molecule. Now, this is often complicated. If we have oxygen in the empirical formula, we ignore it. Don't worry about it. Okay? And you'll see why when we propose a couple structures. If you see a halogen, okay, we just equal that with a hydrogen. We'll just add another hydrogen there because they're monovalent like hydrogen, okay? If we have a nitrogen there, we actually take off a hydrogen, okay? So let's have the rules up here and let's go through some examples. Keep track of degrees of unsaturation with some real things. Okay, so if you're given this empirical formula, C8, H12, how many double bonds or rings do you have in a proposed structure? Well, the max would be what? 2n, 16 plus 2, 18. 18, then minus 12 divided by 2. How many do we have? 3, right? So 3 double bonds and or rings are present here. So let's see. How about this structure? Would this be a possibility? You don't need to count up all the hydrogens, but at first you should just to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. And how many double bonds? 1, 2, 3. Okay. So it works there. Each time you introduce a ring or a double bond, you're taking like 2 hydrogens, right? That's just one possibility, right? There's many others for this structure, this formula. How about this one? Would that also be C8H12? Yeah. 2 bonds, 2 double bonds, and 1 ring, okay? And you could come up with some others too. So this suggests what are the possible structural isomers for that empirical formula. And lets you know right away how many double bonds or rings you should be thinking about. So it's a very useful idea. How about this one? C7H11Br. Now how do we deal with that? Well, again, the bromide's the same as a hydrogen. So what do we have here? And what's our max here? 16, right? Minus 12 divided by 2. So what do we have? I think it's 2. Everybody see that where we got to 16? That was 2 times 7 plus 2. And then 12 here. Bromide is just added in with the hydrogen to get to 12 there. Then 2. So what do we have here for possible structures? Oh, how about this one? One of many, right? So we got a ring and a double bond. And you don't even need to count up the hydrogens. You know it's correct, but you should go through that and figure out a couple. How about this one? Have a couple double bonds instead. And then the bromide, we can move the bromide all over and that will be good. How about this one? C4H10O. And this kind of shows you why you ignore oxygen. Because when you have an alcohol, it's like inserting the oxygen into a carbon-hydrogen bond to make an alcohol, okay? Or an ether, okay? But there we take off 2 hydrogens, make a ring or make, 2 bonds to a carbon. So let's see, we don't even need to think about, so how many degrees of unsaturation do we have here? 10 minus 10, we have 0. Okay, so what would be some possible structures here? Well, what about that one? Yep, count them all up. I think you got the 10 hydrogens there. You can see this is oxygen just inserting in there to make that. Of course, this would be one, but you could tell right away that this would not be one. Why? Because that has a ring, right? And that has 8 hydrogens, not 10. So it tells you right away. How about nitrogen? Let's do one with nitrogen. Let's see. How about C5H11N? This is because when you have an amine in the molecule, you insert nitrogen into a carbon hydrogen bond, and then you have to add a hydrogen to get to the neutral amine, right? Think about the structure. So we're taking off here. So this should be what? 10. And this should be 12. What? Minus 10 over 2. So how many double bonds or rings? Just one. So can you draw some proposed structures here? Well, what about here? There you go. 1, 2, 3, 4, 5. Yep. And count up your hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And that's just 1 degree of unsaturation. How about another one here? You can have that in a ring. And I think that's the same empirical formula, but obviously a different constitutional isomer that is kind of suggested, I think, by the structure quite clearly there. Questions on that? We'll use that more when we get to NMR and mass spec, okay? But it's a useful concept, this degree of unsaturation idea. All right, naming. Now, naming X and alkene. So this X is a number out in front. The parent is still alkane. We modify the alkane parent name. We always look for the longest linear sequence, right? Now we have an alkene in there, and this number refers to where the alkene is. And it's where it begins, and we have to number through the alkene, both carbons of the alkene, in order to be complete here. So what do we have here? We have butene. And where does it start? It starts at the 1 position, 1 butene. Now, do we have 2 butene? Of course. And that's this one and this one, right? Now we need another designation here, right? 2 of the groups here, and each carbon has 2 different groups on it. So now we have to keep track of geometric isomers, cis and trans. And notice the bigger groups are across from each other. So that would be trans 2-butene, and this one would be cis 2-butene. Is there a 3-butene? No, that's a nonsense name. Why? Again, the rule is give the lowest possible numbering. Now, we have some numbering issues here. Alcohols still have higher priority than alkenes, okay? And alkenes have higher priority than alcohols and halides, okay? So we do have some priority there. Alcohols, alkenols, so I'll show you some examples of that. There we give the lowest priority to the alcohol, okay? How about this one? Okay. So our longest chain is what? 1, 2, 3. Is it a propene? No. 1, 2, 3, 4, 5, 6. Is it a hexene? Yep. Hexene. And the 1 position is where the hexene is. And then what else is on there? Well, circle your parent if you need to. That'll help the substituents stand out, right? So at the 2 position, you have a methyl. 2 methyl, 1 hexene. Do we need to worry about cis or trans here? Are there geometric isomers? No, this carbon here has 2 hydrogens on it. Those are the same. Remember, for cis-trans geometric isomers, both carbons need to have 2 different groups. This one does, okay? There's 2 different groups there on that carbon. But here there's 2 hydrogens, okay? If we exchange those, we get the same molecule. So we don't need cis or trans there. Okay, how about this one? So we'll come up with a name. Let's see if we need to worry about stereoisomers here. Okay. So we got a chloromethyl, 1, 2, 3, 4, 5, 6. Okay. So it's still a hexene. And the first thing you do is get the lowest number to the alkene. So it'd be 1, 2, 3, 1, 2, 3. So it's 3 hexene from either side. Now, what side do we number from? 1, 2, 3 chloro or 1, 2, 3 methyl? What do you think? Chloro and why? Alphabet, right? So we alphabetize the others, and that's how we break the tie there. So this would be 1, 2, 3, 4. So let's get the name on there. And so it's 3 chloro, 4 methyl, 3 hexene. Are we done? Let's see. Examine each carbon of the alkene, and are they both with 2 different groups? Yeah, this carbon here has a methyl and an ethyl on it. Okay, 2 different groups. But the other one has to have 2 different groups before we worry, right? And this one here has chloro and ethyl. So yeah, we need to worry here. Now, these have 4 non-hydrogens on them. We could use cis and trans descriptions easily if we always had a hydrogen there to talk about, because whatever else was on there had a priority over hydrogen. But now we need to prioritize ethyl over methyl, okay? And we do that by the periodic table, and we get the priority here. Well, carbon-carbon, both the same, but this carbon has another carbon on it. So priority-wise, this is 1, this is 2, okay? So we have to go through this operation to figure out the alkene geometry now. And now we get chloro versus carbon, which is higher in the periodic table, chloro. This is 1 here. This is 2 here. If 1 and 1 are together, okay, that's called Z, okay? And that's similar to cis, but this comes from a German term called Zusammen. Any German speakers, missionaries out there? No, I'm sure there's some in the class. There's Zusammen means together. Okay. If 1 and 1 are across from each other, that's E or entgegen. Okay. So we need to use these more specific terms when we have non-hydrogen groups here. So tri and tetrasubstituted alkenes. You can apply E and Z to normal 1,2-butene, 2-butene. The trans one would be E. The cis one is Z. Okay. So they still apply. But the IUPAC rules, if you have 3 or more groups on a carbon, double bond here, you have to apply that. So what is this? 1 and 1, the top priority groups are together, so this is indeed Z. Z, 3 chloro, 4 methyl, 3 hexene. Now you could generate the E form of this easily by just exchanging the ethyl with this methyl, or the chloro with this ethyl over here. And that'll give you the E. Okay. Sorry, that's kind of a strange thing, but it's the convention here. Let me show you another strange thing here, which has to do with the cis ones. Now, cis ones are cyclic ones, cyclopentene, and like I mentioned, the small, medium-sized rings are always cis. So we don't need to say cis cyclopentene because trans cyclopentene is not known. It's not a big enough tether to accommodate the trans. But what is something we need to worry about now is this. Is that 1 methyl cyclopentene or is it 2 methyl cyclopentene? Well, we number here, 1, 2, and we always number through both carbons of the alkene, okay? We do that for the parent one, the acyclic ones, and especially it's important to do it for the cyclic ones. So this is the 1, this is the 2 position. Why isn't this the 2 and that the 1? Well, it's the lowest possible numbering. So this is what? Simply 1 methyl cyclopentene, okay? What about this one? Let's just move the methyl over. We already said if the methyl is over here on this position, that would also be 1-methyl cyclopentene. We just number the other way. What about this then? Is this 1,2-methyl cyclopentene? Or what do we need to do here? 1, 2, 3. Is it 3-methyl cyclopentene? Yeah. So 1, 2, 3. We have to number through both carbons of the alkene first, regardless of what substituents we have on there. So this is what? This is 3. Okay. Which begs the question, is there such thing as 2-methyl cyclopentene? Or is that just an incorrect name? And why? Well, yeah, if we just had this over here, okay, that would just be having the number out, right? Well, could this be 2-methyl cyclopentene? And we just number here 1, 2. No, because then we get around here. 5 would be the other carbon of the alkene. We have to number through both carbons of the alkene. So actually, this is an incorrect name. There's no such thing as 2-methyl cyclopentene or cyclohexene, whatever. Okay. So it's either 1 here, or it's 3. Oh, is there a 4? Is there 4-methyl cyclopentene? What do you say? Let's think about that for a second. Some people say thumbs up, others are wavering. What is there such a thing as 4? Yeah, okay. What would it look like? Look like this? Or we'd have it there, right? And number it. 1, 2. We got to number through both carbons. 1, 2, 3, 4. Yeah. Is there such thing as 5? No, that'd be the same as 3-methyl cyclopentene. So this idea, this rule of numbering through both, okay, so number both carbons of an alkene, okay, and they're always 1, 2, okay, and then whatever the substituents are relative to them, give the lowest number there. Yeah, question?
I'm trying to remember, like, around a month and a half ago, we were talking about, like, the cyclic alkene versus, like, it has a really long straight chain. If you have, like, a cyclopentene, but you have, like, a 6-carbon chain next to it, is that GKE numbered?
Yeah. So we can have a big substituent here, okay? And if that's a longer chain, more carbons than the number of carbons in the ring, then we name that as the parent. It's whichever has the largest number of carbons. We'll work some more examples. We're out of time right now, so we will pick it up right there. We'll show you the interesting alkenes, but we'll get into the big 5, okay? And what are they, right? Hydro.